Hello, everybody. This is for going through the question 33 in chapter 2 in algebra section for the course Maths1152 at the University of New South Wales. Now, in this question, we have two plane equations. One of them is given by Cartesian form, and one of them is given by parametric form. And we would like to find out the intersections of these two planes. So clearly, we need to turn one to another. You can turn to the Cartesian form to the vector or vice versa. So if we turn the vector form into the Cartesian form, it works better because we will have a linear system of equations and we know how to solve it. Okay, so we would like to turn this presentation to the Cartesian presentation. Solution. We would like to, there are two ways I'm going to do that. One of them, the first way is a long way, and this is not preferable. And the second way is the preferable one. So let's do what you can do. You can say, so this is the x vector here, the position vector is x1, x2, x3. So the first row reads at x1. This is what I'm doing. So x1 is equal to 6 minus 2 lambda 1 plus lambda 2. So this is from the first row. From the second row, you have x2 minus 2 lambda 1, lambda 2. From the last row, you have x3, 3 plus hello? Yep. Okay. Then from the last row, you have 3 plus 3 lambda 1 minus lambda 2. So we would like to solve these equations. We would like to basically get rid of the lambda 1 and lambda 2. We want to find out an equation depending only x1, x2, x3. This is what's the Cartesian form, right? So what we can do, we can take these two equations and add them up. Then you will get rid of the lambda 2. Then you will find an expression with respect to lambda 1. So that's what I've done here, right? That's 4 lambda 1, and you add this part, you have x2, x3, and that's minus 1, and you found lambda 1. When you put lambda 1, you can put it back here. Then you will have an expression and with respect to lambda 2. That way, you will have two expressions, which are lambda 1 and lambda 2. Then you use any equation, put it back, and find an equation only depending on x1, x2, x3. That's what I'm doing here. Okay. When we substitute lambda 1, lambda 2 into the second equation, for example, then tidy up the equations because you have a 4 here multiplied by 4. Get the unknowns on one side and the constant term on the other side. Then you will have this equation. It is a Cartesian form for the plane P2. Now, what else you can do? You can use a normal vector. You can calculate a normal vector and find a Cartesian form. Well, since it is given by vector form, so this is the directional vector and this is a directional vector. This two directional vector is on the plane. So the normal vector is any vector which is perpendicular to your plane. How you calculate it, basically you take any two directional vector and cross product them, it will give you the normal vector. So by that way, you will calculate only the normal vector and tidy up the equation. It is much, much straightforward than the first method. Let's do that and you will see. Now we would like to compute, that's what I said already, normal vector, which is just, and then use the normal vector into this equation. This is the point form representation for a plane. This is the normal, that is normal vector, that is dot product. This is the general position vector, x1, x2, x3. And this is any point on the plane. Since we have a dot product here, so dot products give us a number. So since this is a dot product, we require this one to be 0. not the zero vector. This is very important. Be careful what you're writing. The dot product gives you number, not the vectors. If you write a vector notation here, it is incorrect. It is not correct. Okay, what is let's call this directional vector u, let's call this directional vector v. This is our P2 plane. I will show a long way to calculate the normal vector, and I will show the simpler way to calculate it. Actually, they are always coming from the definition. So this is the long way. It's the usual way by using the definition of determinant. This is by using the definition of the cross product. So normal vector is given by the u and v. So I, j, k will be the first row. We will calculate the determinant, and the second row is the u vector, minus 2, 1, 3, minus 2, 1, 3. And the last row will be the row vector of v, 1, 1, minus 1, basically transpose of this. Okay, so we would like to calculate a determinant. When you're calculating this determinant, you're opening up the determinant definition with respect to the first row. So what it requires, so I is an entry, I is a vector, which is the I, j, k are the standard vectors, as you know. And I is the vector, and the position is the first row, first column. So the coefficient is +1. And the determinant, when you remove from these yellow ones, the determinant of this matrix is here. That's what we need to calculate it. And then J is the first row, second column. The entry is J, and the position is -1, first row, second column. And then that will give us a -1. And the determinant, when we remove first row, first column, the matrix left, the matrix left is -2, 3, 1, -1. We need to calculate this determinant. Last entry, first row, third column, that's k. The entry is the vector k. And we will calculate the determinant when we remove the first row, third column, and 2 by 2 matrix here left. That we need to calculate the determinant of it. So that's -1, 1, 1, 1. Okay, when we calculate the determinant of 2 by 2 matrix, as you know, we multiply the main diagonal entries, 1 minus 1, minus, negative, minus this times this. So this is -1, -3, and that's I. We have a coefficient -1. This is why we have minus here. And this times this is +2, minus, because it's the opposite diagonal, that's -3. This is where it's coming from. That's k here, k, determinant of this matrix. This times this, minus this times this. So that's -2. Opposite diagonals gives you the -1. So we have -4i, j, -3k. So as a vector form, that's -4, 1, -3. So this is a proper way to calculate the normal vector, but there exists a shortcut. What is this shortcut? Same idea, but we will do it in one line with your eyes. You need to get used to it. You need to practice it. Your brain needs to get used to the idea. For the first row, exactly then whatever it is here, you will calculate the determinant of this one. So this times this minus this times this. So this is -1, -3, -4. And now for the second one, so this is this needs to be minus, which is coming from this position. And you remove this row, on the left, the matrix left here, -2, 1, 3, -1, which is this matrix. You need to calculate the determinant. By removing this times this is +2, -3, that will be 1. But when you're multiplying -1, that will be 1. And then removing this one, you have -2, 1, 1, 1. And you calculate the determinant, this times this, minus this times this. So this is -2, -1, that's -3. That's exactly the same vector. So you can do this, you can do this, but you need to understand the proper way of doing it. And then you practice the shortcut for your exam time. Why it works? It works because the determinant of a matrix is equal to determinant of the transpose. What we are doing here, we are taking the transpose of this matrix. The transpose of this determinant, transpose of this matrix is this matrix. So this determinant is exactly that determinant. That's what we are having there. It works because determinant of any matrix, any square matrix, is equal to determinant of the transpose of that matrix. That's, you have a property of that. Okay, so once we know the normal vector, we can put it in. The position vector x1, x2, x3, and you have a point, any point, but the simplest way to get the point is just from the reading of the presentation. So this is a point on the plane. Take it simply. You can choose any point on the plane, but why you need to work more just if you have something in your hand to use. This is a dot product, and this is our normal vector, position vector, on the point on the plane. So this dot product gives us 0, -4 times this, 1 times this, plus -3 times this. That's -4 x1 plus 24, x2 plus 2, minus x3 plus 9 is equal to 0. If we organize it, this is the Cartesian form of the plane P2. So we obtain a Cartesian form of the plane P2. So this is one equation. This is another equation. So P1 and P2 planes are intersect. If and only if we can find a solution, simultaneous solutions for this linear system of equations with these equations. So you have 3 unknowns and 2 equations. Our expectations, if there exists a solution, most likely it will be an infinite solution. We have all possibilities, but well, we have the possibility that P1 and P2 could be empty. That in that case, you have no solution. If you have a solution, then one of them needs to be free, then you will have a line. Because if you think about that, you have a plane in the 3-dimensional space, you have another plane in 3-dimensional space. They intersect, either they intersect on a line or they don't intersect at all. Okay, so we would like to write it down, this linear system of equations, A as AX is equal to B. A is the coefficient matrix, X is the unknowns, and B is the vector on the right-hand side. So the coefficient matrix 8, 8, 1, 4, -1, 3, and so on. So what we want to do, how we solve a linear system of equations, we practiced before. So we write down the augmented matrix first, and then we apply the row operations. We would like to get the reduced row echelon form. It is enough to get row echelon form. I prefer the reduced one, which means that you would like to get an identity form in the left-hand corner when you induce the system. The augmented matrix, the efficient matrix, and the right-hand side vector. Now, we would like to apply the row operations. So we would like to make this position in 1. That's the first thing. So let's multiply the first row with 1/8. And now you have this position, you want to, this position is 0. That means that if you multiply the row 1 by -4 and add to this one, we will get this position 0. So that's what we do. So when we looked at here, this is 1, 0, this is what we want. So we are getting the coefficients, leading coefficients. because our aim is to get on the left-hand side corner is the identity matrix or the form of an identity matrix. Then we have a -5 here. We would like to make this position now 1 because that's the leading coefficient 1. So if we multiply this by -1/5, we will get this position 1. That's what we do. And then now we have this matrix. So this is 1, this is 1, this is 0. It's perfectly fine if but I want to get an identity matrix in this corner. So I want to get this position 0. It is enough you can go back to the equation form after this because this is the row echelon form. But if you want to get to reduce row echelon form, you want to make this position 0, like an identity matrix in a corner, in the left-hand corner. I prefer this because it give me less work when I go back to the equations. So this is why I like it. So I want this position 0. And so in order to be able to do this, you multiply this by -1 and add to the above line. So these are the numbers. As you see, it gives me directly the solution. So what I mean by that, I see x1 and x2 depending on an x3. So x3 is a free variable. So let's say x3 is equal to lambda. So this is the constant terms, and we are taking the x3 lambda on the other side. So x1 will be x3 over 8 minus 5 over 8 because this one goes to on the other side, and lambda represents the x3. So x2 will be minus 7 over 2, and this one will go to on the other side of the equation. That will be plus, so that's plus 1 over 2, while x3 will be lambda, and x3 is lambda. So x1, x2, x3 is basically the coefficients, 6/3 over 8 minus 7 over 2 and 0, and the minus 5 over 8, 1 over 2, and lambda. So if you take lambda is equal to 8 mu, and then you will have some constant, you will have integers or for the coefficient of your parameter. So this is why I'm doing this. Because presentation, there are infinitely many ways to present it. So I have the integers as a presentation here. This is why I take the lambda is equal to 8 mu. So 8 mu will be the 8 and will go on, and then I will have 4, and the last one 8. So I can also get rid of this form into making a looks like a integers. You can do that. If you choose mu is equal to 3 over 8, sorry, then you will find another point such that P1, this point is intersection of P1 intersection P2 because it satisfies this equation. 6 minus 3, 2 is the point, and minus 5, 4, 8 is the directional vector for the line, which is the intersection of these two planes. So P1 and P2 intersect on the line given by this parametric equation. So there are infinitely many solutions. There are infinitely many presentations for this because mu runs through every real number, and the real numbers are infinite. So this presentation is infinite. We prefer to have simpler versions and some integers in the presentation to make it nice. Do you have to do that? Not really, but it is nice to do it. Okay, this is the solution for this question. Thank you very much. I hope it is helpful for you. It is useful for you. Thank you very much. Cheers.